All right. We're going to be looking at calculating equilibrium concentrations. So this is where we're actually going to put this to work. Got a reaction. We got a K value. Not very high. We start off with so many moles of everything. Again, 1 liter container. So sometimes you need to determine the concentration. Other times it's told to you. Sometimes you have to think of it in pressure form as well. All of these you need to think about as you go through. We want to know the concentration of everything at equilibrium. Now, these are called ICE tables, okay? Initial, change, equilibrium. Sometimes they're called RICE tables with an R because they have the reaction as well. Doesn't really matter what you call them. These are going to be a technique not only are they that they're looking for on the AP, but that's going to be helpful for you for organizing what you're doing. So first thing we need, law of mass action. We got our reactants over our products. Products over our reactants equal to our K value. Okay, no problem. Second, we need the ICE table. So initial, change, equilibrium. Please don't actually write these down. ICE is probably the best you need. So then we kind of use this to line up what each of these are. So initial, we had 8 molar, 6 molar, 0 of each because none of these existed. At some point, there will be some here, and you'll be looking at those later. But for now, there was nothing to start. Now, each of these are going to be used up with a coefficient of 1. So that means these are going to change with a decrease of some concentration, and these are going to increase with a change of concentration. The values that they're going to be at equilibrium is our original minus the change for each of the reactants, and then the change for the products. Always check your volume, always check how much you're given before you even get started. So then we solve for this equilibrium. We plug in our values. We have x squared over this value here of 8 minus x and 6 minus x. Now you might say, how do I determine x is equal to 4? Now, the way you can determine that it's 4 is doing some quadratic equation stuff, which you'll see me do some examples upcoming. You can also make some approximations, but we can't do it with these values being so large. The idea here is though you determine what x is equal to, then you plug in x equal to your equilibrium amounts. So therefore, I know at equilibrium, we've got 4, we've got 2, we've got 4, and 4. So that's the basis behind this idea, these 3 steps. Step 2 is going to be your hardest part. But there's a few ways you can make that a little simpler, as read in the book, and as I'm going to go through a few of these. Okay, so I've got a reaction at equilibrium. I've got a Kp, because these are gases. I've got partial pressures in atmosphere, so I don't need to do any conversions. The temperature is not relevant, except that K does change with temperature. We'll talk about later how, but that's not relevant for us, but you're always going to see a temperature. Kids always want to do something with some calculation with the temperature. Leave it alone. Just walk away. So we're looking for the equilibrium partial pressure once equilibrium state is achieved. I got my RICE table started, reaction, initial, change, equilibrium. So initially, I have this, this, and this. My coefficients are all 1, so my changes are going to be subtracted for the reactants, added for the products. And so my equilibrium as such. Products over reactants. Now I look at this and equals to 4.56. You do some algebra. You should be confident with your algebraic skills. If not, we can talk about those one-on-one. In order to determine, you have a quadratic equation, an A, a B, and a C. Now with these A, B's, and C's, this is what we're going to use for our quadratic equation. Now, if you have a graphing calculator, you know how to use it, awesome. That'll save you tons of time. If you don't, or if you do have one and you don't know how to use it, I'll show you very simply. Super easy, can save time. If not, you need to remember this guy. Now, this is not always going to be the case. There are approximations that you're going to learn in the textbook, and you can see on AP Classroom that can speed things along, but you might have to do one of these on the test. You never know what they're going to throw at you. All right. Now, again, throwing in your B, your 4AC, doing your math, you get 2 values. Okay, that's true with any quadratic equation, right? However, only one of them is going to make sense. Okay, we look at our first one, 0.934. Looking at me throwing it back into the equation, there's no way I can use more than I've ever had. So I know that doesn't make sense. A smaller value? Yeah, I can use less than everything that's present. So that's the only one that's going to make sense. I plug it into my equilibrium values and get my answer. Another example. Now, this is a great one that can be thrown at you, and you try to just answer the question because you've done lots of these, and you answer the wrong question. Don't do that. Okay, so we've got a reaction. Boom. Not so bad. I can see I've got a solid here, so that's not going to play a role in my KC here. Okay, not going to play a role. So that's not going to play it, even though they tell you the mass of it. We have a volume. In this case, it's a liter, so it makes it easy. Could be 2 liters, makes it all different. We have moles. If we add an additional 0.07 moles of H2, how many moles of HI are produced when the equilibrium is established? Note, how many moles are produced when the equilibrium is reestablished? Not what's the final concentration, so keep in mind with that. So we first need our Kc, products over reactants. I know it's molarity, so boom, I've got my Kc. So simple way to determine it. My rice value, a rice table. Got my rice. I started off with 0.0234. I'm adding 0.07. Okay. Nothing with the iodine. I'm going to cross it off so I don't mess that up. And I have so much hydrogen iodide. I see it's a 1 to 2 ratio. So 2x for every 1 here. I've got my equilibrium values as present. Okay. Products over reactants, I can see this is going to be squared. I'm not going to say I've got this value here. Algebra leads you to get to here. Again, I can show you the algebraic stuff. It's not too bad. It gets a little messy. But the problem is we can't use our assumptions or our changes because these values of K are not very big. Okay, we can do this a lot better with acids and bases and when K is not that large or it's super huge to where this X is going to be insignificant. But we can always fall back on this. And if you have a graphing calculator, it works great. If not, again, we can do it the long way, but you can still do this efficiently. So we have our A, B, and C. I plug that into our quadratic like we had on the previous. And we get X is equal to a positive value or a negative value. Well, negative doesn't make any sense. So I can easily eliminate that. Now, this is my X. The question states how many moles are produced when this is reestablished. So this is what I'm trying to look for. I'm looking for essentially saying how many moles change in that. This is not the question. This is the question. 0.0364 moles are produced of hydrogen iodide. Okay. If we need much more math if this was not the 1 liter volume, because then we need to go, okay, that's the concentration, how that changes, and go to your final moles. But again, this is the question. Don't just put it on autopilot going, boom, seen it, got it, done. Make sure you read the questions carefully. So like I said, quadratic equations, yuck. Sometimes there's perfect squares. So if you have something that's like 5 minus x squared, boom, you can take the square root of both sides. Now you can totally determine it. Other times you have approximations. When k is less than 1, when your x is less than 5% of the initial concentrations. There's definitely some you do in Pearson that do this way. There's also great examples in Pearson that show these as well. These are probably going to be more common than not on the AP exam, but not necessarily. Sometimes you'll have crazy substitutions, rearrangements to where the algebra is really hard, or you could have something cubed for all goodness sakes. Okay? Those are the things that you need to think about as you're looking about it, but practice it to see these same crazy examples. Come in with your questions. Please ask them as I have them, or as you have them, and take care.